Okay.
Yes, doctor.
Okay. So we will continue today solving problems of chapter 2. So first, in problem 5, we have the hydrostatic force F is the same on the bottom of all three containers, even though the weights of liquid above are quite different. The three bottom shapes and the fluids are the same. This is called the hydrostatic paradox. Explain why it is true and sketch a free body diagram of each of the liquid columns. So in this problem, we will see how weights of different liquid fluids of different weights, okay, will act in the same way on a certain shape. So here, what is common between the three containers is first that we have the same area. So the bottom area is the same for the three, okay? So this is common. Another thing that is common between the three containers is the height of fluid, okay? However, the weight is quite different because you have different shapes of your containers. So here I have the same height for the three, okay? So this is H and this is A, okay? And we have seen last time that because we have the same height for the three, okay, then the pressure exerted by the fluid on the bottom surface is the same in the three cases, because you know that pressure is equal to rho g h, okay? Since we have the same fluid in the three containers, so rho is the same, and we have the same height of fluid, therefore we are exerting the same pressure on the bottom surface. And since the area is the same for the three surfaces, then the total force F exerted by the fluid on the surface is equal simply to the area times the pressure. Okay? Now, what seems weird is that the weights of the fluids are different. So how the force will be the same? To understand this, okay, we will do a small free body diagram for each container, and we will see why the force F is different than the weight. So let us start by the first container A, okay? In order to find the relation between F and W, we will take as a system the fluid inside the container, okay? If my system is the fluid inside the container, then I will draw the forces acting on it from all sides. So first, I have here the two inclined sides of this container. These sides will exert on the fluid a pressure that is perpendicular to the surface. So as you can see here, the resultant force will be inclined. So here, of course, it's a distributed load, okay? But at the end, when you want to calculate the total force, you can represent it as we done here by two inclined force perpendicular to the surface. So this is perpendicular to the surface. And always the force of a surface on a fluid is directed from the surface towards the fluid. This is why these two forces are downward, okay? Now, in addition to these two forces, you have the weight of the fluid, of course, and you have the force of the bottom surface on the fluid. And by principle of action-reaction, if the fluid is doing on the bottom surface a force equal to rho gh times A, so by action-reaction, the bottom surface will do on the fluid the same force magnitude, but in the opposite direction, okay? So here, we can say that this force represented here is the force of fluid on surface, on bottom, force of fluid on bottom surface, okay? While here we have the opposite, this is why it's opposite signs. So here we have F of bottom on fluid, okay? And what is common between the two is the magnitude and the direction, only the sense is opposite. So we have the same magnitude here, F. Now we can compare F and W because we know that our fluid is static. So sum of forces is 0, okay? Now, if you look at the horizontal components, I don't have any problem because F and W do not have horizontal components. we only have these two, and these two will cancel out in the horizontal direction. So I only care for the vertical direction. For the vertical direction, I have the weight, and I have two downward force resulting from the inclined surface. And these forces all should be opposed by the force of the bottom on the fluid. So it is very clear from the free body diagram that F should be larger than W in order to have equilibrium. Okay? Now, if I consider the free body diagram of the second container, I take the fluid in the second container. I have here I have vertical surfaces. Because my surfaces are vertical, so they will exert on my fluid actions in the horizontal direction. And these actions, as you can see, will cancel out from the two sides. So in the vertical direction, I only have the weight and F. This is why for this shape of container only, okay, I have that F is equal to W, because my surfaces here are vertical. Now for the third shape, okay, for the third shape, if I draw the free body diagram, I have the resultant exerted by the inclined surface, but here, because of this shape, as you can see, if you draw the perpendicular from the surface towards the fluid, you will get a upward vertical force, okay? And of course, the horizontal components will cancel out. And this is the weight W, and this is F. So as you can see here, you have the weight is downward, but the two vertical reaction of the inclined surface are upward. From here, we understand that F will be, for equilibrium, F will be lower than W, okay? Because these surfaces are helping the bottom in sustaining the weight of the fluid, okay? Any question on this problem?
Yes دكتور بقى بA
Yeah.
بA أنا ما عرفت ليش higher وبC ما عرفت ليش lower.
Can you why it's, can you please repeat, because I didn't hear well.
بA بالvertical عم F و W.
Okay. Here.
وقلنا إنه هي F
Yes.
should be higher than the weight.
Yes.
وبC F should be lower than the weight. بس ما عرفت شو الفرق.
Okay. The difference is that if you look here at your forces, okay, in this case, for equilibrium, you should have sum of forces equal to 0, yes or not?
Yes.
Okay. So here you have the weight is downward, and these two forces are downward. So for F to oppose all of these, it should be higher than W, because look, if I say this force is equal, for example, to small f, okay, and also here I have by symmetry it's equal to small f. If you write the condition of equilibrium, what will be your condition? It will be that weight plus 2 times small f equals to big F. So of course, from this relation, you can say that big F is higher than W. While if you take
okay.
While if you take this case here, the equation will be W minus 2F equals to big F. So in this case, the force F is smaller than W. Okay?
Doctor, I understand. F is downward.
I cannot.
Previous figure.
F is downward in A.
Downward.
In small a, small f is downward, while in C, small f is upward. Okay? Because here, f is upward. Since if you look at your figure, this is the
I mean big F.
No.
I mean big F.
Big F is always up, because here you consider, you should pay attention, what do you mean by F? If you mean the force of the fluid on the bottom surface, it's a downward force, okay? But when you take the fluid as your system, then you put the force of the bottom on the fluid, which is upward. Okay? But both will
Okay.
have the same magnitude. So the magnitude of the force of fluid on bottom, which is downward, is equal to the magnitude of the force of the bottom on the fluid, which is upward. So when you take the fluid as your system, you will put F upward.
Thank you, doctor.
Okay. Any other question on this? Let me-
Yes.
Yes.
Why did you do that? هن سألوا to prove that F is the same.
Yes,
لا
F is
أنا
the
هيك.
same. We proved that F is the same by just saying that because we have the same fluid, so rho is the same. And because we have
Yeah,
the,
okay, the same height and the same fluid, but why did
Yeah.
we do the rest? No, ما
we
طلبوها.
did the rest to understand how, if you just look at the figure without doing an analysis, you will say, I think that F should be equal to the weight for equilibrium. Okay? But when you do the analysis, you will understand that no, F is not equal to the weight. So the second part is just to understand the hydrostatic paradox, okay? Because they told you, sketch the free body diagram in order to prove the hydrostatic paradox, okay? And this hydrostatic paradox will tell you that the shape, even if the shape of the container is different, the bottom, if you have a common area, and you have the same fluid height, okay, and fluid type, then F will be the same, whatever is the weight of the fluid above it. Okay, so you are applying 3 different weights in A, B, and C, while you are obtaining the same force of the fluid on the bottom, which might seem for you weird, but when you do the analysis, you can see why the force is not equal to the weight in all cases. Okay.
Doctor,
Yes.
in both cases A and C,
Yes.
كان عندنا هيدي الفورس اللي هي من السيرفس على الفلويد.
Yes.
نحن عملنا لها بروجكشن على الاكس اكسس والواي اكسس، واللي عملنا لها بروجكشن على الواي اكسس هي السمول اف.
Yes.
Okay, thank you.
Any other question? Okay, so this is for the first problem. Let us move to another one. Gate ABC in the figure has a fixed hinge at B and is 2 meters wide into the paper. If the water level is high enough, the gate will open. Compute the depth H for which this will happen. Okay, so in this problem, this is gate ABC. Okay, so it's our gate here, and it's hinged at B. And as you can see from the figure, okay, it's clear that here, if you apply a couple in the clockwise direction, the gate will not move, okay? Because look here, you have an obstacle for motion. While if you apply a couple in the counterclockwise direction, you will be able to open your gate, okay? This is why they asked for the maximum level of H, that for if you want the minimum level of H to open the gate, okay? Because if H is small, then the force exerted here will not be enough to open your gate, okay? So in this problem, the first step to do is to draw the free body diagram of the gate, because it's my system of interest. I want to determine for which condition it will start to rotate. So in order to open it, sum of moment should be positive, okay, in this direction, in the counterclockwise direction. So the critical height corresponds to sum of moment equals to 0, okay? So I just want to find what is the critical height above which I will start to be able to rotate my gate. So to be able to determine this height, as we said, the first step is to draw the free body diagram of the gate. If I consider my gate, I have 2 parts for this gate, AB and BC. and both are exposed to a fluid, which is water. Okay? Now, in case they didn't give you the weight, you can consider that the weight of the gate is negligible. And if they gave you the weight, of course, you should put it. Okay? So now, I have water here, and I have here, let's say, I want to compute here, I have the atmospherical level, okay? So it's the atmospherical pressure. And if you have covered the material provided by Dr. Nadim, you can see that the atmospherical pressure will cancel out because it will be from this side and from this side, okay? So here you have the atmospherical pressure from this side, but also when you compute the force acting from this side, you will add to it the atmospherical pressure, okay? So then atmospherical pressure will cancel out from both sides, and you will, all you have to do now is to compute the force that is coming from the water fluid, okay? So I have water in contact with BC, and I have water in contact with
Doctor,
AB. Yeah.
along BC, the atmospheric pressure is constant while it varies حتى لو 20 centimeters.
The variation of atmospheric pressure with height can be neglected because the density of air is very small. Okay.
Okay.
So you can neglect change in atmospherical pressure with altitude. Okay. So now let us consider the gate. Okay, we have part AB and a certain part of BC, because yes. Is someone asking a question? Okay, so first, for part AB, okay, we have water that is below AB, and this water will do a force that is upward on AB, because always, when you have a fluid, you have the force acting from the fluid towards the surface, okay? So you have here, due to pressure of water, you will have a certain resultant force to be calculated, okay? So here you have a total force here, F, you can replace the distributed load by one resultant force, okay? And of course, this resultant force will pass by the centroid of your surface, okay? So you can represent it here by a force passing by this point, okay? Now, the calculation of this force needs a small analysis to do, okay? In order to do the analysis for the force acting from this side, how to think? This is the question, okay? I want to find what is FAB. And in order to find what is the value of FAB, I should know what is FAB. FAB is the force of water on the surface, okay? And also using the same concept, I can say that it's equal as a vector. As a vector, it's equal to minus the force of surface on water. Okay, so here I am introducing this idea because we will learn a new concept here, that if we have a surface, okay, we can say that the effect of the fluid on it is equal to the weight of the missing part, and I will explain what I mean by this. So now we will demonstrate together, okay, that the force of the water on the surface is equivalent to the weight of this part, which is missing here. Okay, and we will see why.
Doctor?
Yes?
Do you mean the weight if it was water?
Yes, if it was water, of course. Okay. Here in this problem, we have a simpler approach, and I will do it also for you. But this technique you might need it a lot in curved surfaces, so I will explain. Okay. So, how to demonstrate that the force here is equivalent to the weight of missing water? Okay. To do the demonstration, you can take this part of the fluid. Okay. You can take this part of the fluid as your control volume. Why you can do this? Because if I take this part of the fluid as my control volume of interest, okay, and I want to draw forces on it. So let us say I am interested in this control volume. Then you have this surface is acting, AB is acting on the water control volume with a downward force, which is equal to the opposite of the force I am interested in. So I want to find what is this force F. Okay, this is F of AB on fluid. Okay. Now, from the other side, I have here at this level, okay, I have the force of bottom on fluid. So this is F bottom on my fluid, okay? And how to compute this force here? Who can tell me? How to find the force acting here?
بجيب the pressure with area.
Yes. So it's equal to the pressure at this level. What is the pressure at this level here? What do I have here? I have rho.
Gamma H. Gamma H.
Yes, it's gamma small h. Okay. So I can say that here I have gamma times small h times area, bottom area. Okay. Now, if I consider at this level, at the horizontal level, these two will cancel out. Okay. This part and this part will cancel out because they are in the horizontal direction and they are opposite to each other. And I still have what as a force in addition to these two? I have the weight. I have the weight of this part. Okay, the weight of fluid in this volume. So I can say that from this figure, FAB on the fluid, F of AB on the fluid, by applying sum of forces equal to 0, is equal to F, okay, minus the weight W. And if I replace, okay, if I replace, what is small f? If I want to do the analysis of small f as a weight, the expression of small f is gamma HA. Can you tell me gamma HA is which volume? It's gamma of water, yes or not?
Yes.
Okay.
Yes.
So if you do gamma of water times H times A, okay, it's equivalent to what? It's equivalent to the weight of this rectangle of water, this one, okay? Because if I tell you what is the weight, if I have a water that is filling the whole part, and I want to find the corresponding weight, I will do gamma times the whole volume. What is my whole volume here? It's small h times A. So F is nothing then, okay? If you want, I can replace it by weight of the big rectangle. So it's weight of the big rectangle, okay? Minus, and what is W? W is the weight of this part. So if you want,
دكتور ما فينا نتركها gamma HA؟
بلا فينا نتركها جاما HA بس أنا
يعني
I
gamma
want
of water
yes you can leave it as
و
it is
H هي
but
1
what I want you to understand is that the force of AB on the fluid is equivalent to the weight of the missing volume of water, okay? And we can demonstrate this from here because weight of the big rectangle minus weight of water, okay, will give you what? It is equivalent to weight of missing water. Weight of missing water. So from here you can take it as a rule. If I have a surface and I want to find the effect of the fluid which is below the surface on it, okay, all I have to do is to find the missing part. So here look, water level is reaching this level here, okay? So here we have a part that is missing here. Here we have a missing part of water, okay? So this will be the weight of this part will be equal to, if it was filled by water, okay, will be equal to the force of the surface on the force of the water on the surface. So from now on you can use this formula directly. So if you have any fluid below a surface, okay, and you want to compute what is the value of the force of the fluid on the surface, you can simply say I will complete my volume as if water was here, okay, and then if I calculate the weight of this part, I will find what is FAB. Any question on this? If it's not clear, I will repeat.
Yes, please. Can you repeat?
Yes, please, doctor.
Okay, I will repeat. Okay. What we want to find here, we want to demonstrate that if I have a surface and I have water below the surface, okay, and I want to find what is the force of the fluid on the surface, I can find it directly by saying if I complete, so the level of water here is higher than this level. If I complete my volume of water, if I complete it, I will obtain here, I have a missing part of water. So this is called missing volume of water, okay? Because as you can see here, the level of water here is different than the level here. So if I have, because here water is below the surface, I can consider that if my water was at the same level everywhere, okay, then over this surface I will have this volume. So this part is called missing volume of water, okay, because it's not present here. But why I use this part? Because I can demonstrate that the force of water on the surface is simply equal to this weight, okay? So this part of water has a certain weight, okay? This weight can be calculated as W equals to, what is the volume of water here in this part? If I want to find the volume, it's corresponding to this length, okay? This length in this problem is what I want to find. I want to find how much water will fill, to which level we will have water on BC, okay? So I will call it, it's an unknown, I will call it big H. So let us say I want to find big H. What will be the missing volume of water? It will be equal to H, okay, times H times the area here, okay, the bottom area AB. So it's H times A, okay. Now, and if I multiply by gamma, I obtain, this is the weight, this is called weight of missing volume, okay. Now, why I can say that the weight of the missing volume is equal to the force I want to find? Because if I do a small analysis to be able to demonstrate this issue, I can take this control volume. I can consider now water as my system of interest. I will take this part. Why I take this part? Because here I have at this level, I have the interaction between the surface and water. And what I want to find is what is the force of interaction between the two. Okay? So, because I'm interested in the force at this level, I will consider this control volume of fluid. This one. Okay? Now, for this control volume of fluid, what are my forces of interest? I have the weight of this part of fluid, okay? And I have the bottom force. The bottom force, I can calculate it. Why I can calculate it? Because I know that here I have a pressure at this level. Pressure is equal to rho times G times small h. Okay, so I have rho G times small h. So if I know the pressure here and I want to find the force of the bottom on my water control volume, okay, I will get that F is equal, so the force of bottom on my fluid is equal to rho times G times small h times big A, okay? But if you do a small analysis of this term, rho G times HA, HA corresponds to which volume? If I want to draw it here, so this H times A, if I want to draw it on my figure, is which volume? Is this one. This is my whole volume, okay? Because I'm multiplying this area by small h, which corresponds to this. So this term is simply, if I want to replace it by a volume, is equal to this volume, the whole one here. Okay? Of course, with I can take the volume with the width, of course. So here the width is in depth, so this is my whole volume of interest. Okay? So I can say here from my result that H times A can be replaced by big volume, okay? The volume of the big rectangle. And this volume, I can divide it into two parts. It's equal to the volume of missing water. So it's equal to volume of missing water plus the actual volume, okay? Plus the actual volume of water, okay? So if I want to represent it here, as you can see, this whole volume is divided into two parts. So let me draw it. I have two parts for the total volume. I have this part, and this one I will call it volume of missing water. And I have this part, which is the actual volume I am working on. Okay? So I have demonstrated now that the force of the bottom here, the force of the bottom is equal to the whole volume. So if I say this is part one, this is part two, okay? I have demonstrated that F at the bottom corresponds to weight 1, which is the weight of the missing water, plus weight 2, which is my actual weight, the actual weight of my control volume, okay? So now, when I do the balance of forces, I have From here, I have W1 plus W2. And the weight of my control volume is downward, equal to what? The weight of my control volume is W2. Okay? So I can replace this force, which is the weight of my control volume, by W2. So if I do the equilibrium analysis, sum of forces equals 0. I will deduce that this force, which is the force of the surface on my fluid, to have equilibrium should be equal to what? Should be equal to W1. So this is equal to W1. Okay? So I deduce now that the force of interaction between the surface and the fluid is simply equal to the weight of this part, which is called weight of the missing part. Okay? Is it clear now? Who can give me a much easier way to solve, to demonstrate that it will be equal to W1 without the control volume? So I can directly determine this. Any idea how to demonstrate, how to find the force in another way? Okay, look what we can do. In a much easier method is to consider that this surface is at this level. Okay? So, and because in a fluid at the same level, I have the same pressure, I can say that the pressure that is exerted on AB, okay, the pressure at this level is equal to the pressure at this level here.
Doctor, there's less than a minute.
Okay, Yalla, we will continue in the other session. Just I want to tell you that the pressure here is equal to the pressure here, okay? And I can calculate the pressure here by saying that it's just gamma times big H, okay? So we will continue in the second session.